Hello everyone, let's find out as to what is the time period of a spring mass system. To understand this, let's look at a spring mass system as given here. There is a spring which is assumed to be massless, to which a small mass m is attached. Now let's take some reference point for this system. Let's take the center of the mass as the reference point for this system. Now suppose if a force F is applied onto the object, because of this force the spring would expand. Let's assume that the spring expands from here and goes to this position. It's been pulled towards this end. If you leave it from here, it would oscillate. That is because whenever we pull a spring in a given direction, the spring will not keep quiet. The spring will counter this, applying a force towards the mean position. That force is called as restoring force. Now what is seen experimentally is that this restoring force is proportional to the displacement. With the minus sign here, this minus sign indicates that it's a restoring force, and this is called as Hoax Law. It says that mathematically the restoring force is proportional to the displacement, or we can bring in a constant here saying that restoring force is equal to minus k into x. The minus sign indicates it's a restoring force, and this k is called as spring constant. So this k is called as spring constant. This k tells us about the stiffness of the spring. So it tells us about the spring stiffness. To understand this, let's write what is k in terms of Fs and x. It becomes Fs by x. We take only its magnitude because the minus sign here indicates just it's a restoring force. Now if we need to expand or compress the spring, then we need to apply force F, and that force should be at least equal to the spring force in magnitude. So only then we can expand or compress the spring. We can write this also as applied force by x. Now its SI unit would be Newton per meter. Now to define what K means, let's take if x is equal to 1 meter and consider two different springs. Let us consider a spring used in say pen and a spring used in say lorry. We have seen that the spring used in lorry would be very thick. Something of this kind. It will be very thick. Something of this kind. It's just drawn roughly here. It will be very thick compared to spring used in pen. A spring used in pen will be very light. If you want to extend both by 1 meter, it is obvious that we need to apply a greater force in case of spring used in lorry than the spring used in pen. So greater is the value of F from here, greater would be K, because here x is taken to be 1. So which means that if the value of K is more, it would mean that a greater force is required to cause an extension in the spring, or in simple language, greater is the value of K would mean that greater is the spring stiffness. Now coming back to a problem, if we pull the spring and leave it from here, it would oscillate. Now because of the restoring force, the block would move towards the mean position, but since the force and velocity acts in the same direction, this block would cross the mean position and go to another extreme end. So the block may come to this position. So the block would oscillate between the two extreme ends like this. It should be equal here, so draw it properly. So if this is the mean position, say called as C, we call this as extreme position B and then D. So this spring basically will oscillate between the points B and D. It will go like this, stop and then come back, again stop and then go back. It will oscillate with varying speed. The speed is greater at the mean position and the speed would be 0 at the extreme position. So it will start to oscillate in this case. Assuming that the spring is placed on a frictionless surface and also the block is placed on a frictionless surface, this would oscillate forever. So in this case, we need to find its time period and frequency. To understand this, let's recall the spring force is equal to minus k into x. Now this spring force is the one which is causing it to accelerate. So it becomes m into a because force is seen as m into a, where m is mass of the object, not the spring, because we assume that it's a massless spring. That is equal to minus of k into x. K is a constant for a given spring. Therefore, from here, a is equal to minus of k by m into x. Here, for a given system, k and m both are constant. So we can say let k by m, which is a constant, be called as omega square, where omega is equal to angular frequency. Therefore, a is equal to minus of omega square into x. This is what we get. We'll call it as 1. But from definition of simple harmonic motion, what we get from here is, by definition, a is equal to minus omega square into x or y, any one parameter. Just keep in mind that here it is minus of omega square into some displacement. Now comparing 1 and 2, we can say that 1 is of the form of a simple harmonic motion only. It's very obvious from there also, but then we just want to compare with this. So even 1 is an equation for a simple harmonic motion. Therefore, its time period is equal to 2 pi by omega, but omega from here, omega square is k by m, omega is equal to root of k by m. Therefore, t is equal to 2 pi under root of omega, which is under root of k by m, goes on top. T is equal to 2 pi under root of m by k. So this is the expression for time period of a simple pendulum. In terms of frequency, we know that frequency is equal to 1 by time period. So it will be 1 by 2 pi under root of k by m. So this is the expression for frequency for a spring mass system.